So far we've been talking about electric charges, and we've mostly been dealing with charges that are stationary. We've been dealing with electrostatics. Today we're going to start talking about charges that are in motion. Charge in motion is called current, and we're going to look at this in the context of charges moving through conductors. Now, for the most part, when we've been talking about conductors in this class, we've been thinking of perfect conductors, ideal conductors, so-called superconductors, right? In which, if you apply an electric field across a conductor, the charges are going to instantaneously move around so as to kill the electric field inside the conductor. In other words, the electric field would be zero inside one of these perfect conductors. We're going to be talking a little bit more about imperfect conductors today, right? And an imperfect conductor is something that has what we call resistance, right? There is some resistance to these charges moving around. They can't just instantaneously do whatever they want. So that's an important distinction. And in particular, if I have a piece of this imperfect conductor and I connect it with wires to, say, a battery somewhere, such that I am able to maintain a fixed potential difference between the sides, between this side of the conductor and this side of the conductor. Let's say this is at high potential, and let's say this is at low potential. Now you guys know that the consequence of high V over here, low V over here, the consequence would be that I set up an electric field. And it would point to the left, because electric field always points in the direction of decreasing potential. Now if this were a superconductor, this couldn't happen. The charges would move so fast so as to immediately kill this electric field and kill that potential difference. There's no battery on Earth that can maintain a fixed potential difference across a superconductor. But if the conductor has resistance, then the story is different. In fact, we can maintain an electric field across the conductor. And physically what's happening is inside the conductor we have all of these ions. So imagine this is a really sort of zoomed in view here. Imagine that we have our ions. So here are our ions. The ion, think of as just the part of the atom, or the nucleus and the electrons that aren't free to move about in the metal, right? So that's going to be the nucleus and most of the electrons. Maybe one or two of the electrons are going to be free to move around. And so those are the ions that are effectively locked in place inside the conductor. Now, the electrons, on the other hand, are free to move about throughout the conductor because it's a metal, right? So all of these little green dots here are my electrons. Now, the motion of the electrons inside of a conductor is actually quite complicated. Now, if the electric field weren't there, if there were no electric field here, then the electrons are still going to be bouncing around frantically, right? Because there's heat, right? They're going to have a certain amount of thermal energy related to the temperature, and so they're always going to be moving around, bouncing into the ions, just scattering around in this sort of frantic way. I call this sort of the random motion of the electrons. And if you calculate the random speed of the, or if you know, a typical random speed of an electron in a conductor, even without an electric field, is something along the lines of 10 to the 6 meters per second. These things are zipping around really fast. And that's always going to be happening. Imagine that there is this electric field, right? It turns out that they're still going to be zipping around frantically, but because of the electric field, a given electron is going to feel an electric force that's this way, right? Because electrons are negative and they feel a force in the opposite direction. So as they're frantically moving around, they're going to eventually start bouncing around and making some forward progress. Maybe it's like this. Over the course of the journey, it's eventually going to be moving from this end over to this end. If you measure the speed of electron, you know, essentially how long it takes the electron to travel this distance, it's actually very slow compared to 10 to the 6 meters per second. And so we call it a drift. It's as if the electrons just drift from one side of the conductor to the other. And that drift is on the order of about 10 to the minus 3 to, or 10 to the minus 4 to 10 to the minus 3 meters per second. Very slow by comparison. But the point is that on average, like if you were to take the average random velocity of the electrons, it would be 0 because there would be just as many electrons moving this way as this way. So on average, this doesn't get you anything. This drift motion, however, does. You get a net flow of charge through your conductor. We have current, okay? So at a microscopic level, this is exactly what's going on when we apply a potential difference across one of these imperfect conductors. That is a resistor. As an example, let's calculate how long it takes an electron to get from one end to, say, a flashlight to the other. So you turn on a flashlight, how long does it take a single electron to make it from one end, where the battery is, to the other end, where the light bulb is? And let's say it's about 5 centimeters long. Okay? And the answer, well, you wouldn't use the random speed to calculate this. You're going to use the drift speed, because the drift speed is the only speed that represents any actual forward progress for these electrons. And so the time it takes for the electron to make it from one end to the other would be the distance traveled divided by the drift speed, right? And so that's about 5 centimeters divided by, say, I don't know, let's just pick a value, say 10 to the minus 4 meters per second, which if you calculate winds up being about 500 seconds, which is about 10 minutes. So it obviously begs the question, why doesn't the flashlight take 10 minutes to actually turn on? Right? Well, the answer is because immediately when you turn on that flashlight, you set up this electric field in the whole flashlight. So it's not just the electrons that are close to the battery that start moving, it's all of the electrons in the entire circuit. They all start moving at once, much like water through a great big circular pipe. If you put a pump on one side, all of the water starts flowing at once. Okay, so as I said, current is charge and motion, and whether electrons are flowing this way or positive charges are flowing this way, whether a negative charge is going this way or whether a positive charge is going that way, we define that to be a current to the right. I use the symbol I, and the definition of current will be the amount of charge that passes by a fixed position in space per unit time. So immediately you can check out the units. The units would be coulombs. A certain amount of charge is going to be coulombs, and time is in second. We have a name for coulombs per second. 1 coulomb per second is called an ampere, which we can call amps if you like. We can call an amp, and I shorthand that A. Right? So this is our definition for current. So let's set up a circuit. Let's imagine a circuit with a constant set source of energy. Let's say I have a battery. A battery is a very good source of constant voltage. There's the positive terminal of my battery, negative terminal of my battery. And I attach a wire to the positive terminal and bring it into contact with a light bulb. So here's my filament and my light bulb. And I take another wire and I bring it back to the negative terminal, right? So this is the simplest circuit that I can possibly think of. Our battery is what provides the energy here. It provides a constant potential difference between the positive terminal and negative terminal. That's maintained by the battery. That's the battery's job, is to provide that fixed potential difference, right? And so I'm going to list some general properties here. The potential difference between the positive and negative terminals of the battery, we have a name for that. It's called the EMF of the battery. EMF stands for electromotive force. Don't worry about that too much. But we shorthand that as a script E, right? So E, a script E, not to be confused with capital E for electric field or energy. A script E is specifically going to refer to the potential difference that a battery maintains. Now, why do I give this, why do I even bother, right? If I'm using this idea of EMF, if I'm using a script E, it implies that there is a source of energy involved. There is something there providing that fixed potential difference, right? A delta V, there doesn't have to be a source of energy. I can just take any two arbitrary points in space and measure a potential difference delta V, but that doesn't mean that there's some source of energy between those 2 points, right? That's what the E implies, right? So typically when you see an E, it means we got a battery. You don't have to do this. Again, remember choosing the zero of potential is arbitrary, but I tend to like to say that the top of the battery is positive E and the bottom of the battery is 0. If I'm free to make that choice, I just tend to do it, just because it helps keep things straight in my head. Okay, now, in the circuit, which includes the wires and the bulb, in the circuit, the current is always going to flow from high potential to low potential. So in this case, the current is going to flow this way. Through the top wire, it's going to flow this way through the bulb, and it's going to flow this way through the bottom wire. In reality, when I say that current flows this way, more than likely what's happening is that electrons are actually going from the negative terminal up through the bulb and into the positive terminal. Again, that's just because Ben Franklin chose wrong. However, inside the battery, so let me write that down. So in the circuit, the current flows from the positive terminal to the negative terminal. It's different in the battery though. So in the battery, the current flows from the negative terminal to the positive terminal. So inside the battery, the current actually goes up this way. And you can see that that's actually in the exact opposite direction than the electric field would have those positive charges go. Again, when I think of current, I tend to think of it as the flow of positive charge, even though in all likelihood it's negative charge flowing the other way. It's completely equivalent. So you can think of this as negative charges, or excuse me, positive charges going from down here to up here. But inside the battery, the electric field must be pointing down, because positives are up here and negatives are down here, right? The electric field must be pointing down, yet the battery is able to take positive charges and effectively bring them uphill, right? So you see what I mean about a constant source of energy. It's able to provide that energy by lifting those positive charges up the potential hill, right? That is the job of a battery. By the way, where does that energy come from? Well, it comes from chemical energy inside of the battery, right? Maybe it's a cadmium, maybe it's a lithium battery, I don't know. But the energy is stored somehow in the chemical compound that's inside there, and that's translated into electrical potential energy as it brings the charges from the bottom of the hill to the top of the hill. One other thing you'll notice here is that the current is the same at all points in my circuit. The current is the same at all points in my circuit. Whatever current leaves the positive terminal of the battery must be coming in the negative terminal of my battery. If that weren't true, then we would have a charge conservation problem. If I had more charge leaving than I had coming in, then I would be creating charge somehow, and that doesn't work. That's non-physical. So I must have just as many positive charges coming into my bulb as I have coming out. And so the current at all points inside this circuit has to be exactly the same. It has to be, right? Now, you'll see some exceptions to this if I have like if I start adding other branches and building more complicated circuits, but at least in this very simple circuit, that simply has to be true, right? If I connect things in a great big series like this, then the current must be the same at all points in that series. The last thing I'll mention down here is that all the wires are equipotentials. Every point on this wire is at the same potential that it's electrically connected to over here, positive E. Every point on this wire is at 0, right? Because I've defined it that way. You only get a potential change if you walk across a circuit element. So across the bulb, the top side is high, the bottom side is low. As I'm walking across the battery, coming in this way, it's low and goes to high. So there's a delta V across the circuit elements, but not across the wires, right? And in fact, we've already seen this before, back when I talked about Gauss's law. All conductors are equipotentials. In fact, we're actually making an approximation here. We're assuming that the wires are superconductors, that they have no resistance. It's only the bulb that has resistance in this case. In general, that's not true, but it's a reasonable approximation for many circuits. Okay, so I already mentioned a little bit about a perfect versus an imperfect conductor. And the reality is that some conductors, it's easier to push charges through them than other conductors, right? Some conductors have high resistance, other conductors have low resistance. So I want to talk about resistance. It turns out that for most materials, or for a lot of materials, any material that we call ohmic, this is true, and this covers a lot of materials. But it turns out that for these ohmic materials, the larger the potential difference across the conductor, the larger the current, right? And in particular, we would say that the current is directly proportional to the potential difference across the conductor. So in that sense, we can say that the current is directly proportional to V, and there must be a constant of proportionality over here. You can think of V as the cause. You can think of I as the effect. You double the voltage, you'll double the current in an ohmic material. So there must be a constant of proportionality here. And in fact, I write it this way. I write it as 1 over R, right? And so written more simply, this would look like I equals V over R, right? Your book, I think your book introduces this equation as V equals IR, but it's the same equation. I just write it this way to show that this is the dependent variable and this is the independent variable. As I change V, I get different I's, right? And so this, in fact, has a name. This is called Ohm's Law. And this R, which if I solve for it is just V over I, is a new constant that has units volt per amp, right? Volts per amp has a name. We call that the ohm, which I give the Greek capital letter omega, right? So that is resistance. If a certain material has large resistance, then for the same voltage, I'll get less current, right? If it has very low resistance, a superconductor would have 0 resistance, which means that for any voltage, I would have infinite current, which is non-physical, which is why I mentioned before that, that no battery, we can't make a battery that can do that. Our universal circuit symbol for a resistor is something that looks like this. If I draw a wire and a squiggly line like that, then I mean I have one of these imperfect conductors. Right? And so in fact there's a simple way of redrawing the circuit that I just showed you. In that situation I would have a battery that has some EMF like that, and then my light bulb would have some resistance, and I can finish the circuit like that. So this is that simple circuit that I just drew you, written in more standard circuit notation. And so if I set this circuit up, then immediately current is going to flow like this, right? A common misconception is that as I push current through the resistor, it somehow gets eaten up by the resistor. But again, that's not the way this works. There's just as much current coming in the top as there is leaving the bottom. That has to be true, again, from charge conservation. What's different on top and on bottom is the potential. The potential is high up here. The potential is low down here. What affects the resistance of a conductor? If I build a conductor and I want it to have a certain resistance R, how do I do it? Well, I have several options. I can obviously use any geometry I want when I'm building a conductor, and I can make it out of whatever I want. And both of those things absolutely affect the resistance of my conductor. Let's say I have a cylinder, right? And let's say my cylinder has area A, that is cross-sectional area A, and let's say it has some length L, right? It turns out that if I make the length of my conductor very, very long, then that's going to increase the resistance. And the reason is, as I make this conductor longer and longer, I'm putting more ions in the way. There's more stuff in the way for the electrons to get through. So as L increases, R increases. Right? That's just a general property. If I increase the area, imagine an analog. Imagine this was a pipe. Right? Is it easier to squeeze water through a small constricted pipe, or is it easy to push water through a nice big pipe? Right? It's certainly easier to do the latter. And so the same is true for charges, for electrons as they're moving through this thing. So as the area increases, the resistance will actually decrease. If I build this blob out of rubber, then I'm not going to be able to push any charge through it at all because rubber is an insulator. If I build it out of gold, then I'm going to, electrons travel very freely through gold. And so that would make a very low resistance. So it absolutely is important what you make this out of, or what you construct this out of. And every material has its own what we call resistivity, which we give the Greek letter rho. Now, resistivity is different than resistance. Resistance depends on the geometry of the conductor, whereas resistivity is just a property of the conductor itself. When you put all this together, you find that the resistance is equal to rho times L over A. And you see this has all the characteristics. As A goes up, R goes down. As L goes up, R goes up. And as the resistivity of the material goes up, R goes up. Now again, resistivity is just a property of the material. You can look it up in a table. For example, for copper, it's 1.72 times 10 to the minus 8. By the way, what units would it have? Well, units of rho, in this case, if you multiply R times A, you would get ohms times meters squared. Divided by L, you get ohms meters squared divided by meters, which is ohms times meters. And so, like I said, for copper, it's 1.72 times 10 to the minus 8 ohm meters. For something like rubber, a good insulator, it's a huge number, 10 to the 13th ohm meter. So you can see the resistivity is something that can vary by many, many, many orders of magnitude, right? And all of these things affect the resistance of the material.